Okay, good morning, everybody. Thank you for joining us. My name is Chris Edson. I'm the education specialist here with Brookside Laboratories. Brookside, we're in western part of Ohio, in New Bremen, Ohio, in the United States. We are a part of the Amplify network. So Amplify is a large consulting network of approaching about 200 independent sports, turf, and agricultural crop consultants. Kind of sharing information, we work together, and this network also has access to Brookside Laboratories. So the Amplify network is sort of a three-tiered approach or a three-pronged approach of the consulting network, and then we've got Brookside Laboratories that handles all the testing services here in Ohio. We do have a lot of accreditations in geotechnical testing. We do a lot with sand-based media and putting green surfaces and things like that, but also chemical analysis. We have environmental testing, a lot of pesticide, herbicide screenings, and then sort of the third tier that we have, sort of a new part of Amplify, is the Nutrient Star program. So what Nutrient Star is, it's a sort of a science-based, independent, sort of third-party review program for nutrient management tools. So we work with companies that have products that they're doing nutrient management on, and we're sort of third-party verifying the efficacy of these tools and how well do they work. So that's sort of the three different approaches that we have. And this morning we are joined by Dr. Micah Woods. Dr. Woods is the founder and chief scientist of the Asian Turfgrass Center. His PhD was done at the Cornell University here in New York, working with Dr. Frank Rossi. Shortly after that, working 2001, 2005. Oh, I'm sorry, that was when he was doing the PhD, was 2001 to 2005. After that, worked with turf grasses all over the world. A big collaboration with Dr. Larry Stoll, who's on the call today, Pace Turf out there in California. They've done some of this work together on the MLSN approach, which Mike is going to present on. So again, thank you for everybody joining us this morning. Thank you for Dr. Woods for joining us. I'm going to go ahead and mute my mic now to cut down the cross chatter. I'm going to pass over screen sharing capabilities to Micah, and he's going to take over from here.
All right. Good morning or good afternoon or good evening, everyone. Thank you so much for joining this event so we can talk about the MLSN guidelines and how they work, and talk about supplying just the right amount of nutrients to the grass. I want to start by showing a couple pictures from the Asian Turfgrass Center research facility, which I had just north of Bangkok. I did this for 4 years, from 2006 through 2009. And I want to tell a little story about something that I saw there. This was in January of 2008, and this picture was taken on March 9th of 2008. We had all different kinds of grasses grown on different kinds of soils. And this was 2 days before we had a field day in 2008. And I'm going to focus on what we called Area 5, which was right over there, the area that's still in green. And this is at Area 5. So this is 2 days later on March 11th, 2008. This area is Manila grass, Zoysia matrella, grown in a sand root zone, and it had a pH of 6.3, and the soil potassium tested 2 weeks earlier was 39 parts per million in Area 5 in that section of the research area. And at the field day, I'd put out some potassium and no potassium fertilizer. I'd put out some phosphorus and no phosphorus fertilizer. I'd put out some iron and no iron fertilizer in these little square plots in between the white paint dots. And if you notice, you can't really see any response at all. And it doesn't mean that potassium's not important, or phosphorus is not important, or iron is not important. What it means is that there was already enough of those elements available to the grass in the soil, and so adding more as fertilizer did not give any plant response. And this was before MLSN. This was during a time when we would look at what I'd call the conventional guideline. The conventional guideline for potassium would be about 117 parts per million. So the idea with the conventional guideline is that if your soil is having a potassium level below 117 parts per million, then you'd have a 50% chance of getting an immediate response to the turf. So I think you've all probably seen something like this. Now, I'm in this seminar today, I'm going to talk a lot about potassium just for consistency, but this applies to all the elements. And I think you've probably seen this where you've done some kind of testing, and perhaps it was potassium, or perhaps it was phosphorus, or perhaps it was calcium or magnesium. The test results came back and suggested that the element was low in the soil. However, you would find that the turf was performing very well. And that means that sometimes those guidelines aren't quite working the way they should. So I was quite aware of this, but I didn't really have a good solution. So I was just kind of making up my own guidelines. At that time, I was saying 50 parts per million for potassium was probably okay. But clearly this grass is perfect, and it's growing with potassium at 39 parts per million. So 39 parts per million in this case was sufficient to produce good turf. So this kind of stuff was happening a lot, and we needed a solution. And I think MLSN is an excellent solution to this type of problem. And I'm going to explain today how that all works. So in today's presentation, I'm going to have 4 main topics. One is the objective, just looking at what I would define as an ideal nutrient recommendation. And then the second section, I will talk about the development of the MLSN guidelines, saying or showing and demonstrating just where the MLSN guidelines came from, where those actual numbers come from. I will work through the procedure of what the nutrient recommendations are with MLSN. And the final section, I will show the results. What happens when we use this method? I suppose that everybody that's watching this already knows what MLSN is. I'll just say here it stands for Minimum Levels for Sustainable Nutrition. And we just call it MLSN. And what it is specifically is a modern method for interpreting soil tests and making fertilizer recommendations from those, specifically for turfgrass. Before I go any further, I want to point out a few other resources that are available to learn about MLSN. So if you are watching this today and you say maybe you'd like to learn some more, or if you think that what I've explained today is a bit bewildering and you'd like to hear it explained in a different way, or if you'd like to read about it, I would like to suggest these documents and these videos. One of them is a seminar that I gave for TurfNet, which was a 10-minute seminar and 50 minutes of question and answer. There's also a video or a screencast that I did based on a presentation that I gave at the European Turfgrass Society in 2018 that puts MLSN in a larger context of making fertilizer recommendations for turfgrass in general. And there's also the Humbug movie, which I think is fun to watch at least once, that includes me explaining what MLSN is. And also I talked with turfgrass managers. I talked with Larry Stowell about how the guidelines were developed and how they're actually used in practice. And as a document that you can read, I highly recommend downloading the MLSN cheat sheet, which is 2 pages packed with all the information about how it works and lots of answers to frequently asked questions. I've done a blog post today and put direct links to each one of these on my webpage. So if you go to www.asianturfgrass.com, you will find direct links to each of these. So to now get started with this for real, let's look at what the objective is when we're trying to make nutrient recommendations. When we're making nutrient recommendations, I don't want to have deficiencies. So I want to ensure that the grass is supplied with all the nutrients that it can use. And I would define all the nutrients that the grass can use as the minimum amount of nutrient to supply, because I don't really want to mess around with deficiencies. So the minimum amount to apply is all the nutrient that the grass can use. But we don't want to waste anything either. So if we're adding more nutrients than the grass can use, or if we're adding more nutrients than the soil can hold, that's a waste. So what we want to do to set a maximum on how many nutrients should be used, we also want to supply the grass with all the nutrients that it can use. All the nutrients that the grass can use turns out to be the maximum amount to supply also. If you'll notice what I've done, I've just defined the minimum amount of nutrient to supply and the maximum amount of nutrient to supply as exactly the same thing. And that's how I think of nutrient recommendations for turfgrass. There is an ideal amount to apply, and I call that just the right amount, or just what the grass requires. If we're adding more than the grass requires, or if we're adding less, I think that's less than ideal. So that's the background of where I'm coming from with this, trying to find a way to make those nutrient recommendations as accurate as possible without having deficiency, and at the same time without having waste. That was a very short section. Now we move on to one that's a little bit more substantial, and that is the development. Where do the MLSN values, where do these values actually come from? Well, they come from a large set of soil test results, soil data from samples that were collected from good performing turf. Each one of these images that you see here is one of the sites, one of the many sites from which samples were collected that was included in the original MLSN data set. And it's a lot more than just these sites, but the main thing to realize is it's a large data set, more than 16,000 soil test results. Each one of them is from good performing turf. It's different countries, different management styles, different soil conditions, different climates, different grass species. It's all professionally managed turf, and the main thing is that we have paired samples that are all from good turf. So the turf was good, and we have soil test data from them. This was a collaboration between ATC and Pace Turf, Wendy Galernter and Larry Stowell, and we've had a fun time working on this since we started on this in 2011. It's maybe the winter of 2011 going into 2012. So we'll start looking at some data now, and these are each one of these points on the chart represents an individual soil test result which was taken from good performing turf. This is 16,163 soil samples, and they go in date from late 1991 until the summer of 2014. So I show on the x-axis here, the first samples were in the early 1990s. It goes up through 2000 through 2010. After I graduated from Cornell and started the Asian Turfgrass Center, I started collecting samples. So this is from 2007, 8, 9, up until 2014. You can see we don't have any data in the MLSN data set beyond the middle of 2014. And I've been threatening or mentioning in the MLSN newsletter many times that it's about time for me to do an update on this. And I fully intend by the end of 2020 to fill in more data, maybe drop out some of the, I'd like to drop out some of the older data, add in some newer data, and update the guidelines. But across the horizontal x-axis here, we're looking at potassium by the Malic-3 extractant. This is in units of milligrams per kilogram or parts per million. And all these samples were tested at Brookside Labs. All of them are tested by Malick 3. All of them are 10 centimeters or 4 inches in depth. All of them are from good performing turf, and the orange ones are representing the ones that were collected by Pace Turf, and the ATC samples are the ones that were collected by ATC. Now, this is the same chart, but I've just put all the points in the same color, so now they're all in purple, and we're not showing a distinction between the Pace Turf samples and the ATC samples. So what we can do, instead of looking at this as a time, instead of looking at these samples were collected in 1991, these samples were collected in 2000, these samples are collected in 2010, we can count up how many samples were close to zero, how many samples had, for example, 20 parts per million, how many samples had 200 parts per million in this large data set of 16,163 samples. So if we do that, this is now showing those same samples, but instead of individual points, we're counting them up. So if you see 200, it looks like there were about 35 or 40 samples at the 200 part per million level in that large data set. But to develop the MLSN guidelines, what we did with these data, and again, I'm just showing potassium here as an example, but we worked through these same process, that we did the same process for each of the elements. So we first did a filter for pH, and I'm always going to recommend that people manage turfgrass with a soil pH that's 5.5 or above and 8.5 or less, because there's some reasons that you can expect to have good turfgrass performance between those pHs, and you can expect a chance of some problems if you're below 5.5 or above 8.5. So we didn't, even though those samples were in the data set, they were collected from good performing turf, we didn't want to analyze them. So we filtered the data and got rid of those samples. So now we're left with 15,414 samples from good performing turf. But there's something else that we didn't really need to work with. We know that some of those samples have ample nutrient holding capacity. They're high fertility soils. And of course, they have plenty of nutrients to supply all the grass requirements. We don't really care about those soils either, because what we want to do is look at the soils that would have a chance of being responsive to potassium or to the other nutrients that we were looking at. Specifically, we wanted to look at sand root zones, which are commonly used on high performance turfgrass around the world today. But if you look at some of the conventional guidelines for nutrients, it seems like the numbers that are recommended are more suitable for high fertility soils, for soils that have a high cation exchange capacity. So we did another filter, and we removed all the samples that had a cation exchange capacity above 6 centimoles of ionic charge per kilogram of soil. So now you'll notice that the x-axis and the y-axis have been rescaled, and we're now looking at 3,683 samples from good performing turf with that pH filter applied, and we've also applied a CEC filter for cation exchange capacity to only look at the low nutrient holding capacity soils, because we make the assumption here that if we can have good performing turf in low nutrient holding capacity soils at a certain level of nutrient, then we fully expect that if the soil has more nutrients than that, the turf will also be supplied with ample nutrients. So by doing this, we're able to fine tune the look at what's happening in the soils that have a relatively low nutrient holding capacity. And soils with this type of cation exchange capacity are very typical of sand root zones or of soil root zones that have been top dressed with sand for a number of years. And it's also relevant, I think, to note that if you would look at the conventional guidelines, and we can find those in a book like this. This is Turfgrass Soil Fertility and Chemical Problems, or I often refer to an article that was published in Golf Course Management magazine in 2004 called Clarifying Soil Testing Part 3, I believe, and that has a table of all the conventional guidelines at that time. If you look at those guidelines for calcium, magnesium, and potassium and convert them into units of charge, you would get a CEC of about 5. So what they're saying is the soils that, even with the conventional guideline, they're saying that the soils that have a CEC of 5 centimoles of charge per kilogram or higher, they're not really expecting a response to nutrients. So anyway, that's what we were working with. These 3,683 samples, all from good performing turf. And then I've overlaid here something called the empirical cumulative distribution function, or ECDF. And what this shows for any level of potassium in the soil, what percent. You'll see the axis on the right side, of the chart shows the percentage. That percentage means what percentage of samples in the data set are at that level or below. So for example, if we look at 100 part per million potassium, that's intersecting this ECDF line at about 75%. So in this data set, about 75% of the samples are lower than that. And what we did is, instead of working specifically with this, we fit a probability distribution to each one of these elements, and we found that a log logistic probability distribution fit very well. And this next chart, you may notice that there is a green line that almost exactly fits on top of that pink line. That green line, the green line is not calculated from these data. This is calculated from the log logistic distribution and simulated data from that distribution. So by working with probability distributions, we can be a little bit more general, calculate a few more things, and we're not really tied to these data exactly. And we're saying that we expect that soil potassium on good performing turfgrass sites should be distributed approximately like this. So we're working with this type of curve of nutrients, and I show on here the conventional potassium guideline, which is 117 parts per million. And I would like to point out that this kind of matches what I showed in that story at the very start. That story at the very start, I said, here we have perfect turfgrass, and that was at 39 parts per million potassium. But the conventional guideline says, if you don't want to apply potassium fertilizer, you need to be safe, you need to be at 117 parts per million or higher. And this is something like 83% of the samples, 83% of the samples in the ATC data set here are below that conventional guideline. If you can see, the count of the data peaks somewhere less than 100 parts per million. So we've got all these samples, thousands of good samples from good performing turf. At the time the sample was collected, the turf was performing well, and it's all below the conventional guideline. So to come up with the MLSN guideline, we picked a number, and the number that we picked was 10%. So we picked the number where 10% of the samples would be below that level. We pick the number for each element. We fit this kind of a curve, and then we picked the number for the MLSN guideline at which 10% of the samples, even though they're producing good performing turf, we just said, let's give us a buffer from what the real minimum is. Even though we know that we can have good performing turf below this level, let's just throw those away and pick the minimum as the 10% level. In the case of potassium, it turns out to be at 37 parts per million. So if we just look at the MLSN guideline is the vertical line there, we threw away the samples that are below that. So we just said, if you're managing turf, the way that you do it with MLSN is you don't want to be below that. Even though we know that you can have good performing turf below that, we don't want to be at that level. And we're very, very confident that if you stay to the right of that minimum, if you keep in this range where there's thousands of samples of good performing turf, thousands of soils producing good performing turf, we are confident that we'll have good performing turf, and you wouldn't be limited in that element. So that's where the MLSN numbers come from. And as we get more data, and as I mentioned, I think in 2020 it will be a good year to do an update. So we may see slight changes. I'm going to move on to the next section now and talk about the procedure of actually making nutrient recommendations with MLSN, because I see in the turfgrass industry, some people do this in a way that I think fails to grasp how this works, because we can't just look at the number and say it's okay or it's not okay. Because if your grass is alive, and I hope everybody's managing grass that's alive, it's growing. And if it's growing, it's using nutrients. And if it's using nutrients, then the soil test level, the nutrients that you have in the soil today are not going to be the same nutrient levels that you'll have in the soil tomorrow. The nutrient levels should go down if the grass is growing, and especially if you're harvesting the clippings. So I'm going to explain how we can work through the calculations to make nutrient recommendations with MLSN to make sure that we stay above that minimum guideline. It requires three numbers. The three numbers that we're going to use are the expected plant use for the recommendation time. By recommendation time, I mean, are we making a recommendation for how much fertilizer to apply for tomorrow, or how much fertilizer to apply next week, or how much fertilizer should we apply until June 30th, or how much fertilizer should we apply in the next 6 months or the next year. So we look at the recommendation time that's explicitly built into these recommendations. We also need to use the number that's the MLSN minimum. That's just one part of this, but we look at the MLSN minimum. That's an amount that we're going to keep untouched in the soil. The way that this works, if we're saying that the minimum is 37 parts per million, what that means is we never want to drop below 37 parts per million. So we always want to keep at least 37 parts per million, excuse me, in the soil. And that's specific to potassium. Again, I'm using potassium as an example. And the other number that we need is the soil test result right now. We need to take these three numbers. So I often refer to them as A, B, and C, where A is the site-specific estimate of plant use, and B is the MLSN guideline, and C is the soil test result. And it works out, if you think about it, that we have an amount that we need, and the amount that we need is, certainly we want to make sure we have the amount that the grass uses, so that's A, and we also need to have the amount that we keep as a reserve in the soil, and that's B. So those need to be added together because that's the amount that we need. We need plant use and we need the reserve amount in the soil. And then we also need to consider how much is actually present, and the amount that's present is the soil test result. So if you take the amount that you need and you subtract the amount that you have, or the amount that's present, you're left with the fertilizer requirement. So it's very simple. You just take A plus B minus C, and you're left with the fertilizer requirement. And that fertilizer requirement already has built in whether you're making a fertilizer recommendation that will be valid for 1 day, or valid for 5 days, or valid for 1 year. And that's based on how long is the duration of your estimate of plant use. I show some tables here. In reality, we would never do it this way, because we're going to let a computer script or Excel file or something like that, a spreadsheet, would make these calculations, and you'd put in some equations. But if we look at the expected plant use, so we can say this is the value A, the expected plant use. I just show you how this works. We can look at nitrogen amount, and we know that we always want to have healthy grass. I've updated this. I've just been doing some monthly tissue testing over the last year from good performing turf, from bent grass, and I come up with these ratios. So for every 1 pound of nitrogen applied, or every 1 pound of nitrogen the grass uses, you can expect that the grass would be using 0.4 pounds of potassium, 0.1 of phosphorus, 0.04 of magnesium, and so on. This is for bent grass, and one would adjust this for other turfgrass species. And if you happen to have data for your own site, you can also adjust that. But I think this is pretty typical for the modern bent grasses and the way that the bent grass is managed today. So if we have, for example, 2 pounds of nitrogen used by the grass, then we would expect about 0.8 pounds of potassium to be used. So this is where we get the value for A. So if I want to make the calculation for potassium, I'm going to take this kind of number, how much potassium is used in relation to nitrogen. And then this is the exact same chart. I've just shown the units in the units that I actually prefer, which is grams per square meter. If you're somewhere in the world that likes kilograms per hectare, you just multiply these by 10. So 5 grams of nitrogen per square meter would be 50 kilograms of nitrogen per hectare. And so these are all the units in grams per square meter. If anybody is really interested in these, I've also made the slides available for online viewing or download. You can also see the link there through my website. And then we take the MLSN minimum number. This is the amount that we always want to keep in reserve in the soil, at least this much. So this is this can be tricky, because I think not everybody always makes the conversion between parts per million to pounds per 1,000 square feet or grams per square meter. But this is how you'd make the conversion, with the assumption that the soil depth is 4 inches or 10 centimeters, and that the bulk density within that zone is 1.5 megagrams per cubic meter. So in that case, it turns out that potassium, if there's 37 parts per million in the soil, that's equivalent to 1.1 pounds of potassium per 1,000 square feet, or 6 grams of potassium per square meter. And then we look at the soil test result right now. I always like to look at the soil test result in parts per million or milligrams per kilogram. In the United States, the soil testing parts per million is usually expressed in terms of weight, milligrams of whatever element was tested per kilogram of soil. In some other countries, I think in the UK, it's common to see soil test results expressed as milligrams per liter. So I think in that case, they're expressing it in terms of volume of the soil. So you have to be a little bit careful about exactly what you're looking at. But in this case, if we're taking milligrams per kilogram and converting it to pounds per 1,000 square feet or grams per square meter, this is the type of numbers you'd be looking at. So all we have to do is take the soil test result, take the MLSN minimum, and make an estimate of plant use, do this for each element, and we can get an exact fertilizer recommendation that should keep us above the MLSN guideline. And in addition to keeping us above the MLSN guideline, it's also going to achieve the objective that I mentioned, which is to supply just the right amount of nutrients. It's going to prevent deficiencies while at the same time avoiding nutrient excesses. So once we have those numbers, we can express the amount required as fertilizer by taking A plus B, the amount that we need, subtracting C, the amount that we have, where A is the amount that the grass is going to use. We want to make sure we apply that, so that we add, and the amount that we want to keep in reserve, that's the MLSN minimum. We add that to the grass use. So we're saying we want to make sure that we supply 100% of grass use, and in addition to that, we want to keep this buffer amount that's untouched in the soil. That's the MLSN minimum. So we add that too. We take those two numbers, the amount that we need, and we subtract from that the amount that we have, the soil test result. So for example, if we're going to take, let's say we have a soil test result today of potassium, and the potassium was 100 parts per million. And let's say, now I have to go back and see what that is. So if the soil test result was 100 parts per million, that's 3 pounds of potassium per 1,000 square feet. So that's what we have. And if we would take an expected plant use of, let's say we're going to use, or we expect the plant to use 2 pounds of nitrogen per 1,000 square feet, let's say between now and the end of September. And that would be equivalent to 10 grams of nitrogen per square meter, or 100 kilograms of nitrogen per hectare, which seems like a reasonable number. So that's going to use 0.8 pounds of potassium. And if we're using 0.8 pounds of potassium and the MLSN amount is 1.1 pounds of potassium, if you have 37 parts per million, that works out to be 1.1 pounds of potassium. So you take 0.8 plus 1.1, that comes to 1.9. We need to have 1.9 pounds of potassium, and we subtract the 3 pounds that's actually present. It turns out that if you have a soil test result for bentgrass with 100 parts per million potassium today, and you're expecting the grass use to be 2 pounds of nitrogen or 0.8 pounds of potassium in those healthy bentgrass plants between now and the end of September, the fertilizer requirement for potassium using the MLSN guideline is 0, because the result of A plus B minus C comes out to be a negative number, which means the amount that's present in the soil exceeds the amount that is required by the grass, and still safely keeps a safe buffer in the soil. I want to close now by talking about the results. What happens, what we can expect to happen when using this method. And I think 3 things come to mind of what we can expect to happen. One is we can be confident that we're going to supply 100% of plant use because we're explicitly making that calculation and including the 100% of plant use in the fertilizer recommendation. We also can be confident that we'll keep a reserve amount in the soil that we know can produce good turf. And that's because we add the MLSN minimum, the amount that we already know is safe. We already know it has an extra buffer in it because we've thrown away the bottom 10% from the MLSN data set. So we've already thrown away the bottom 10%. We've moved the minimum up from whatever the real minimum is, because we realize we can't really find that out. so we're just saying as far as we know, this is going to be safe. We know it's a little bit of a overestimate, but we'd rather err on the side of applying a little bit too much fertilizer to prevent deficiency. We'd rather do that instead of having deficient turf sometimes. And we also can be quite confident that we'll avoid unnecessary applications. So the example I'm going to use is from beautiful Keiya Golf Club in Fukuoka, Japan. This is a golf course that's just over 50 years old. The golf course superintendent is Andrew McDaniel, and he took this photo. And this is a beautiful golf course that I first visited in 2012. And when I visited Keiya Golf Club in 2012, this is a picture from one of the putting greens, and it turned out that there was a lot of moss growing on the putting greens. There wasn't a lot of grass on the greens, or it would be nice to have a little bit more grass and a little bit less moss. And this, the grass on the greens here is Zoysia matrella. In Japan, that's called korai. Andrew McDaniel started as the golf course superintendent there in 2013. And this photo was taken in the spring of 2013. And you can see that one of the first things that Andrew did when he got there is make a treatment to control some of that moss. And there still wasn't very much grass on the green, but this was in the spring. And I'm happy to report that by the summer of 2013, there was a lot more grass on the greens, and the conditions were much better. And I'm going to show here now in these charts, I'm going to show a time series of photos, and I'm going to show how the potassium changed over time. The top chart here on the right shows the soil test potassium in milligrams per kilogram or parts per million. And I've put a horizontal line there on the chart. I've put a horizontal line here to show the MLSN minimum for potassium, which is 37 parts per million. So the first soil tests in the spring of 2013 showed that the potassium on average in the putting greens was more than 60 parts per million. Andrew applied about half a pound of potassium that year, and the grass grew quite good. So in 2014, the grass was very good, and the potassium in the soil stayed above the MLSN minimum. And the grass in 2015 continued to improve, and the potassium in the soil continued to stay above the MLSN minimum. But now the fertilizer recommendation got shifted up a little bit because, as you can see, the soil potassium was trending down. And then the next year in 2016, the grass was also very good, and the soil potassium had gone up a little bit. And then in 2017, the grass was even better, and the fertilizer amount was kind of flattened off, and the soil test potassium was still staying well above the MLSN minimum. And in 2018, the soil test remained well above the MLSN minimum, and the grass continued to be superb. And in 2019, the grass continued to be very good, and the soil test potassium stayed also above the MLSN minimum. So if we look at what happened over 7 years, the total amount of potassium applied was 7.4 pounds per 1,000 square feet, or 37 grams of potassium per square meter. And I think that was the amount that was, it's a reasonable amount there. The soil was always sufficient in potassium in terms of staying above the MLSN minimum, and it just seems like a reasonable way to fertilize. The turf grass performance was excellent, and those are the type of results that I think you could expect. I see there's a question. Should I take this question now, or should I continue? Okay,
Go ahead. Go ahead and answer that now. That'll work.
okay. So all I see in the chat is I'll ask him to clarify that in a minute. I don't see the actual question.
Oh, I'm sorry. That was okay. So the question was, are we looking at this in just elemental K and P? Or are you talking potash and orthophosphates, or this is just K and P, correct?
This is that's a great question. What I'm talking about here is elemental K and P. So I'm not talking K2O. I'm not talking P2O5. So if you want these amounts shown on the chart here, the potassium applied to the greens increase. Well, just what do you multiply it by? I always do divide it by 0.83 to get K2O. So this is elemental.
Thank you.
You're welcome. Okay, I've got another question. I'm just going to go ahead and answer this question. My question is in the A plus B minus C. Over what time do you calculate the plant use? In what period, season, or months? And so the question is, what time period do we want to use? Generally, I recommend to people for turfgrass, I generally recommend to soil test once a year, and I generally am making a fertilizer recommendation that I'm going to base on an annual basis. However, the principle of this is that it's if you want to make a fertilizer recommendation for the next 2 months and you plan to test again in 2 months, you can do that. But I generally am recommending to people to test once a year. So I'm trying to make a fertilizer recommendation from now until the next time of soil testing. If people are soil testing once in the spring, once in the autumn, then I would recommend to make the fertilizer recommendation up until whatever the next time of sampling is. Okay, I think that's the question so far. And you'll notice here that the phosphorus, the elemental phosphorus applied was 0.2 pounds per 1,000 square feet over 7 years. So you might imagine that the phosphorus was relatively high in the soil, and it was. So the next slide here shows that the turf is still excellent, but this is the soil test phosphorus on the greens that started off approaching 200 parts per million when we did the first testing there in 2013, and that soil test phosphorus has now come down to less than 100 parts per million. So there's probably still a few years to go before P would need to be applied. And those 2 phosphorus applications that were made, one was in 2013, one was in 2017, came along with some granular fertilizers that had low amounts of phosphorus in them. They weren't applied because phosphorus was required. It was just the product that was applied happened to have a small amount of phosphorus in it. So it's quite nice using MLSN. If you do happen to have a relatively large amount of nutrients in the soil, you can just let the grass use those and still have excellent turfgrass performance. So those are the type of results that I would expect when using MLSN. I think that we're almost certainly going to be supplying 100% of plant use. We're almost certainly going to be keeping a reserve amount in the soil that we know can produce good turf. And as much as possible, we're going to be avoiding unnecessary applications, because these guidelines are based on modern soils. They're based on the way turfgrass is managed today, and they're based on all the calculations that I showed you earlier, in which we're trying to set a floor that's a safe floor, a safe minimum level that we know can produce good turf because we've seen it at multiple sites all around the world with all different kinds of grass. And then we just make fertilizer recommendations to make sure that the soil stays above that. So that's how it all works. And if this was confusing at all and you'd like to see this explained differently, or if you're intrigued by this and think that this was pretty interesting and you'd like to learn more, I have plenty more information at my website, asianturfgrass.com, and in particular, those four things that I showed earlier. 3 of them are videos. 1 of them is a cheat sheet. Those are packed with lots of information, and in each one of those I've explained this in a slightly different way. So I think by looking at this in so many different ways and trying to explain it or learn about it in different ways, it may be possible to come to a fuller understanding of this topic. I'd like to thank everybody for joining today. Thank you for your time, and I'll be happy to answer questions as long as there are any more.
Thank you, Micah. Dr. Woods, I do have quite a couple of questions that kind of came in, I think, privately or a private chat to me. The first one is we're asking, are paste extracts tests taken into account, and is there a concern of phosphorus or other nutrients being tied up in the soil and unavailable to the plant?
No, I'm not looking at paste tests at all. I would look at paste for salinity. So I think a paste test for turf grass would be valuable if we have salinity problems and we're trying to really measure what the electrical conductivity is or what the sodium absorption ratio is of the soil solution. I don't really look at nutrients that way at all, because we can call Mehlich 3 a soil test, but another term for soil test, a technical term for a soil test, is a nutrient availability index. So if we do a soil test for potassium, to answer the question, it's about phosphorus, right? So I'm not concerned about phosphorus being tied up in the soil if I do a Mehlich 3 test for phosphorus, because the number that we're getting back from the Mehlich 3 test is a nutrient availability index. So it's already looking at the relative availability of that nutrient, and then we just compare it to the guideline. And if people want to make it more complicated than that, and if they don't want to trust the results of the soil test, then I question why people are soil testing at all. And I say, just don't worry about the soil test. If you have a complicated chemical situation and you're not going to trust the results of the nutrient availability index, why don't you just calculate 100% of plant use and just supply that as fertilizer? So now we just ignore the soil, just make the assumption. If you don't want to trust the soil test, you can make the assumption that the soil can supply nothing. Just make the assumption that 100% of the nutrients are unavailable, and then just supply it as fertilizer. Just supply 100% of plant use. Or if you're really, really concerned about it, supply 110% of plant use or something. If people would do that, just look at how much the grass is using and just supply 110% of plant use, that would actually turn out to be a reduction in how much fertilizer is applied to turf grass today, because the previous conventional guidelines for nutrients have been so high that people are trying to hit these target levels in the soil that are completely unreasonable. So I think that answers that question. I see another one here, but I'll let you keep asking the ones that I haven't seen yet.
Yeah,
and then I'll answer Rick's later.
Yep, actually, that was the one that I'd had in the private chat window. I did have a thought though. One thing on this. So just sticking with the example that we used for the most of this on potassium, knowing about nutrient interactions and things like that. Now, with I think the calcium MLSN levels around 350 or 340, I don't remember off the top of my head, but let's taking into account an interaction between calcium and potassium, is there any sort of shift in a potassium level away from 37? Would you maybe move it up to 60 or 70 if you have, excessive calcium? So does another nutrient ever affect where you might want to go? So maybe a threshold, if we're between 500 and 600 calcium, the 37 potassium is fine, but if you've got 1,000 or 1,200 calcium, would you ever consider a slightly higher level in potassium just on those interactions?
I haven't looked at that specifically, but I can say that with the data that that I've been working with over the past decade or so, and basically making recommendations using MLSN, we've had calcium up to 1,000 parts per million in sand root zones, and no, I haven't ever made any adjustment. That's something that somebody could look at.
Yeah, thank you. Yeah, I guess, yeah, that's about what I've got. If you've got a
okay, so yeah, so Rick mentions irrigation water chemistry, seasonal rainfall. He thinks he doesn't like these numbers for bentgrass. So yeah, I mean, most of my recommendations are for bentgrass, and we don't really have any problems. But if people don't want to use these guidelines and want to apply more fertilizer, that's certainly fine. And to talk about irrigation water chemistry, I've blogged about this quite a bit. I think a lot of sites, I mean, most sites, you're going to get 100% of your calcium requirement from irrigation water. That's from a turf nutrition standpoint, not dealing with salinity or specifically dealing with sodicity. But as far as all the calcium that the grass will use, you would get that from the irrigation water. And even potassium, it turns out that I was looking into this. I had a blog post about this, I don't know, a couple months ago. Normal irrigation water apparently has like 20 to 60 parts per million potassium in it. And if you irrigate with just a little bit of that water, you're going to end up supplying 30–40% of the grass's potassium requirement just through the irrigation water. So I didn't mention that, but this is certainly something that should be considered, and you can actually reduce these levels even further if you want to account for what's in the irrigation water.
All right, well, thank you for that. And I think not really a question here, just Nico's got a comment there, just thanking you for the time and the good presentation. So again, I'd like to second that from Nico. So thank you, Micah, for taking the time to do this with us today. We really appreciate it. Thanks to everybody for taking the time out of your Friday morning or Friday evening, depending on where you are. So thanks again. And with that, I think we'll just wrap it up for the day, unless anybody else has any final questions. Oh, no, just a few more thank yous coming through. All right, with that, everybody have a great day.
Thank you.
Thank you.